Hi everyone, my name is Karago and Treasure.
My name is Anne.
And I'm called Humphrey Junior Amapi.
And we are presenting the multimodal acoustic electrical feature extraction framework for machine learning based partial discharge classification under the group code SWML4. With this video, we're going to focus mainly on the model compression. So we're going to briefly introduce partial discharge. Partial discharge is an insulation fault that occurs whereby a spark occurs in the insulation leading to degradation and can lead to fires. Usually occurs in high voltage equipment. So our problem statement, we aim to detect partial discharge, especially in high voltage equipment, and also reduce the maintenance time and enable predictive maintenance. Our research questions mainly look at seeing if the dataset is complete and structurally consistent for both the electrical and acoustic dataset. We look at feature separability, also try to detect features that can better classify partial discharge and detect it. Our contributions were able to train 12 models on both the electrical and acoustic datasets. From the 12 models, we identified 2 models, and from these 2 models, we combined them to form the 13th model, which we use to detect partial discharge, localize to detect where it's coming from, and then to classify the type of partial discharge. So this is our system architecture. We had introduced it. And the dataset description, we used both the acoustic and the electrical dataset. So right now we're going to skip to the model compression. So with the model compression, we selected the spatial temporal graphic neural network. Due to its stability, we do not use the fusion model because of the unstable results. So this was our deployment. So we are going to skip to the model compression. So we had 3 techniques, which included the knowledge distillation, quantization, and pruning. I'm going to go through the knowledge distillation. So knowledge distillation, you usually have a teacher model and a student model. So the teacher model was our original CTGNN model, which is a graphical neural network. So the teacher model usually provides the soft targets, which are the knowledge, and then the student model learns from the labels and then the soft prediction. So basically you're trying to make the original model teach a smaller student model. So how was this student model developed? We began by, our original model had four attention heads. So we reduced the attention heads to 2, hence lowering the computational costs. And the dimensionality reduction, we reduced the dimensionality from 256 to 80. It was done mainly on the classification head and the localization head. So we also implemented a shared trunk. So we combined both the classifier and the localization heads, and which reduced the redundant parameters. We used a lightweight architecture designed with fewer layers and a smaller feature space. So the compression impact. So after training the student model, so we saw that the model size in general used from 500 kilobytes to 81 kilobytes. That was an 85% reduction. The classification performance was maintained. It was still 99.6%. However, there was a degradation in the localization error, which was roughly a 61% error, especially in the mean absolute error. My colleague Ayan is going to take us through quantization.
Okay, thank you very much. On this part, we are going to go through the quantization part. So for this approach, we used what they call PTQ, which means post-training quantization. So this means technically that we did not quantize the entire model. Here, what we did is that we only quantized the fully connected layers, specifically the classifier head and the localization head. So here we kept the GAT CONI, which stands for the Graph Attention Network layers, and the normalization layers of the full float 32 precision. Then the reason why we had to be selective is because the reason also we had to be selective is actually a really important one, whereby we first attempted the full quantization awareness of training the whole thing. And then the model, by then its accuracy had dropped to 33.3, which wasn't very good. So then now we had to change to just quantizing small parts or layers, parts of it. Then that happened because the graph neural network components are not fully quantization friendly. The PyTorch geometric GAT layers use irregular operations. So this means that they break the quantization observers, corrupting everything. So by quantizing only that, the MPL heads and leaving the GAT backbone the way it was, the performance remained the way it was, whereby it was 99.63 according to the table on our right. Then when it comes to our accuracy, our accuracy has actually not accuracy, our localization MAE had increased by 0.0888, which is 60%. And also the RMS has also increased by 0.0140. I'm going to let the next colleague take over.
Thank you, Ayan. The next approach that we employed in model compression was structured pruning. Now, in this slide, we're going to talk about this model compression technique. In that, structured pruning was applied to make our model smaller and more efficient without sacrificing performance. So our main goal here was to reduce the model's complexity and size. And we know very well that in machine learning, larger models often perform well, but they come with high computational costs, and then also a slower inference time, and then they require much more memory. So we wanted to improve efficiency while maintaining high predictive performance. So to achieve this, we used the structured pruning approach. Now, unlike unstructured pruning, which removes individual weights randomly and can create irregular sparsity, structured pruning, on the other hand, removes the entire component of the model. In our case, we removed the whole neurons and then feature channels. Now, this makes the model more compact, then easier to optimize for real-world deployment. So we specifically focused on the graph attention network, or you can call it the GAT. So focus on the GAT layers because they are key parts of our model and they contribute significantly to the complexity. So while pruning, we made sure to maintain the overall architecture so that the model remains compatible and stable. So what we did, we reduced the hidden dimensions within the GAT layers. For example, in both the GAT1 and GAT2 layers, we reduced the feature size. Now, this effectively lowers the number of parameters while preserving the structure of the network. This result of this approach made our model smaller and then also denser. Yeah, it made our model smaller and denser. Now, if you look at the results on the left-hand side, you can see that the accuracy before was 99.63, but then again, after compressing the model, actually remained the model accuracy actually remained the same. So this shows us that even after compressing, reducing the size of our model, the accuracy didn't drop, it remained the same. If you got the file size before was 540.61 KBs, and then after reducing, the size became 142.72 kbs. Now the size definitely reduced, but then the accuracy remained the same. So structured pruning here tells us that our model has been reduced in size, but its accuracy has remained the same. So next slide, please.
To conclude, the spatial temporal graph neural network was used to extract rich acoustic embeddings, and then we used this model mainly because it was stable, and it produced a stable performance. So we acknowledge the IEE data sets and Science Direct publications, and Mr. Galiwango for his guidance and training. Thank you so much.